So today we're going to start my favorite stuff, which is the combinatorics. And we're going to start very slowly. So it's reasonable that the first few lectures, I'm going to go over things that I really hope that you have seen in other courses. In baby algebra, they just touch on elements of probability at the very end of the course. And hopefully you were lucky enough to be in a class that did that. Same thing in pre-calculus. At the very end of the course, they may just touch on a little bit of stuff. If you're in statistics, hopefully you spent actually a significant amount of time talking about counting techniques and probabilities and things. So having this background is very useful, but it's certainly not required because I'm going to start from scratch. Okay, so today we're first going to introduce the concept of probability. This is one of these words that most people have it in their lexicon. They throw the word out all the time, but we're not always sure if what we're saying matches, right, our intent. We'll talk about, oh, what's the probability of this happening? Or I'll hear people talk about, oh, the probability is, 50-50. Like, what does that even mean? No, I think you're referring to the odds. We use a lot of language, and I always laugh because I'm a math guy. And I'm also a statistician. And I love it when people talk about probabilities and then they give numbers that aren't probability numbers. And it's always, like I think in baseball, right? If you get a hit every time up, they say you're batting 1,000. Batting 1,000, what does that even mean? That's actually a term that anybody who's a sports fan, you're familiar with that. Or a quarterback, he's throwing the ball 1,000. Or somebody in the NBA shooting free throws. They're shooting 1,000. 1,000 what? I thought percent was out of 100. So in our everyday life, we use words that don't really make any sense in the context. So we want to make sure we get this. So probability, we have to introduce some terms first. We can't start off with the definition of probability until we define all the things. So the first thing we have is something called the experiment. And this is a very loose term. Now, by experiment, I don't mean you're in a chemistry lab with beakers and smoke going everywhere and you got your lab coat and your glasses. No, not that kind of experiment. The experiment is I'm going to perform something that can be measured. It could be something as simple as I'm going to roll a pair of fair dice. Maybe I'm going to roll them 10 times. I'm going to flip a fair coin. One time, maybe 100 times. I have a deck of cards and I say, pick a card, any card. You've all heard that one. I'm going to sit at a street corner and count how many cars go through each light. And I'm going to do this maybe for the course of an hour. This is the experiment. I'm doing something where I can now count results. That's what it means to be an experiment in probability. Okay. Next thing is what we have is called the sample space. And many of you have heard this term before. The sample space basically is a set, remember order is not implied, a set of every possible outcome. Now, in most experiments, okay, the way we set it up in most experiments, the sample space consists of every outcome and the outcomes are equally likely. And that's very important because that's not always going to be the case. Down the road, we're going to talk about, all right, you only have 2 outcomes and 80% of the time this one's going to happen and 20% of the time this one's going to happen. That's a completely different animal. I'm going to flip a coin and I say the outcome of heads and the outcome of tails are exactly the same likelihood. So that's what we mean by saying equally likely. If I said pick any card from a deck of cards, every choice you could make would be equally likely. So a sample space is a finite list. Now, if the sample space isn't finite, if the sample space is infinite, then you don't really have a problem because you're going to have infinities in your calculation. And that's no, probability can't have infinities. So then the next thing is the event. The event is the particular outcome that you are interested in. So let's keep it simple. We're going to do a coin flip in a moment. So maybe I'm going to flip a coin 3 times. I could have heads or tails at each stage of the way. And then we're going to list every possible outcome when I flip a coin 3 times. I am interested in how many of those outcomes have exactly 1 tail in them, for example. So my event would be all of the outcomes with 1 tail. That's not every single flip because I could have flipped 3 heads in a row, for example. I could have flipped 3 tails in a row. So we start with the experiment to clearly identify what it is we're doing. The sample space is all the conceivable outcomes. And sometimes you can list them. Sometimes you can just express them in words. The event is the particular one you are interested in. Now we can start counting things. So when we say, let's call this, we usually call the sample space big S. And in statistics, we usually call the event big A. It doesn't really matter, but usually they use capital A, capital B, capital C for each event. So NS, this means the number of outcomes in my sample space. N just meaning number. This is, okay, this is a very simple concept. So that number would be a positive integer. Okay, the sample space can't be irrational. It can't have a decimal value. I'm counting how many times, right, I have an outcome. Now, the sample space shouldn't be empty, because if the sample space is empty, then there is no problem. I mean, there was no experiment. You can't have an experiment where there are no possible outcomes. Not a very good problem. Now, here in A is exactly how many outcomes are associated with this event. So now we can define probability. The probability of event A occurring is, and usually the notation we use is we'll use a capital P of A. This is kind of universal, the probability of A occurring, and it's simply the number of ways that A can occur over the number of things in the sample space. This is the universal formal definition of probability of anything you're measuring. Okay, that's why I needed these words first. So I want to do something, I want to find out the probability of the result I'm interested in, then I got to do a little bit of counting first. So let's do some really simple examples here. So let's suppose I'm going to flip a coin. Now, when we say things like, I'm going to flip a coin, you hear terms like, I'm going to flip a fair coin. Now, what does it mean to be a fair coin? That means that the probability of getting a heads and the probability of getting a tails are both 1/2. It is equally likely that I'm going to get a heads or tails. If I flipped a coin that was unequally weighted, for example, then one side is more likely to land down than the other side. Well, then that would not be a fair coin. It's more likely to have one outcome than the other. And everybody here is familiar with the Harvey Dent coin, I hope, right? Harvey Dent coin, I think it's tails on both sides. You know, that's not a fair coin. So we're going to flip a fair coin. Three times. Okay, my outcomes are either heads or tails. So I'm going to write down every conceivable outcome. And my sample space will be the following. And here's the easiest way to represent it. All right, heads, 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 tails. Heads, tails, heads, heads, tails, tails. Tails, heads, heads, tails, heads, tails, 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 heads, tails, tails, tails. We've seen this sort of reasoning before when we were doing our truth tables with truths and falses. Having an order to list them sometimes is a good idea because it just makes it easier to keep track. Now, the first thing you'll notice, there's exactly 8 outcomes if I flip a coin 3 times. There's exactly 8, and every one of these sequences of T's and H's is equally likely. That's critical. If one was more likely than the other, then that would mean we didn't have a fair coin. So here's what I want. I want to find the probability of exactly one tail. All right. So my sample space A will be the sample space, excuse me, my event A will be the event of exactly one tail. So what I want to do next is write down all of the outcomes that have exactly one tail. And that looks like it would be that one, and that one. Looks like I have exactly 3 ways that I could have exactly one tail. So it'd be heads, heads, tails, heads, tails, heads, and tails, heads, tails. So finally, if I said, what is the probability of event A occurring? Well, there's exactly, I'm not sure if I wrote this down the first time, right? It's the number of ways of A over the number of ways in S. I can't remember if I wrote it that way. But the number of ways of A is 3. The number of in S is 8. And we'd say the probability is 3/8. Now, as a general rule, probability is by definition a rational number. Probability is a fraction. Now, there are times when it's convenient to give probabilities to decimal because the individual parts of the problem that you are working with, you might only have decimal values that you're working with. And if you only have decimal values, it's harder to give a rational number as a final answer. But the answer is this. Now, a lot of people will say, well, can I convert this to a decimal? Sure. So I say n is a decimal. I want to write it this way. And then others will say, well, can I write the probability as that? Yes, but percent is not probability. And I find that every student I have ever taught in their head said, no, I learned percent is probability. No, percent isn't a fraction. And percent isn't a decimal between 0 and 1. No, percent is the probability multiplied by 100. No, you don't say percent as probability. That's like scratching a chalkboard. Is it correct to say that 37.5% of the time I'm going to get this outcome? Yes, it is. That's absolutely correct mathematical statement. But in general, you don't give percent as probability because probability is a value. Well, let's see. Where's the value? Do we have a range of values on probability in general? Well, let's see. I am going to flip a coin. I'm going to toss a coin. What's the probability that that coin lands? Wait a minute. If it doesn't land, that means it just kept going up forever and ever and ever and ever. And that's really not possible mathematically or from a physics standpoint. So when I flip a coin, it's going to land. So the probability that my coin lands would be, what would it be if it absolutely is going to happen? Anybody want to guess what's the probability?
1.
1. Oh, okay. Now I'm going to flip a coin. What's the probability this coin turns into a bunny or rabbit and then eats my family? I'm pretty sure that's not possible. So what's the probability this coin's going to turn into a bunny rabbit and eat my family? Probably
0.
Probably 0. Okay, we've just figured it out. For in any conceivable situation, you have a range of values. Probability is always a value that's between 0 and 1. Okay. So, oh, okay. Now we say impossible, guaranteed, if you want to think of it that way. Absolutely certain. So if something is going to happen, there's nowhere around it, it's going to happen, then the probability is going to be 1. If something cannot happen, it's impossible, the probability is 0. So everything else is somewhere in between. It's rare that you're going to work a problem where you get either one of those, but it's still mathematically possible. Okay, it's mathematically possible. When we get into something called conditional probability, that's when you tend to see the zeros. Okay, so that can happen. So this very basic definition of probability allows us now to put a range of values. And if the problem is not too big, it's fairly simple to calculate. Now, here's where it gets a little bit more difficult. You know, some of you guys, for example, like to gamble. Well, the mathematics of gambling is all probability. In fact, we're going to do a lot with gambling. I say this kind of, half tongue in cheek, but I teach gambling when I teach probability. No, I don't gamble. That's, if you want to gamble, that's your thing. But I like using gambling because it gives you something you can perhaps relate to, whether it be playing cards, whether it be, anything. But the concept of gambling is purely based on probability, and therefore the likelihood of an outcome and things like that. What's a good bet? What's a bad bet? For those of you who are poker players or blackjack players, you understand little things maybe about what are good decisions and bad decisions, what are higher likelihoods and less likelihoods. That's all probability based. So I want to start with something like that. Here's my eraser. Now, one of the most simple ways to discuss probability as a practical situation is with a dice roll. Now, the concept, if I have a pair of dice, now a die is a cube with the numbers 1 through 6 on each of its faces. And the other thing is about a die, we always assume a die is fair, because if a die is not fair, that simply means that one side is more likely to land down because maybe there's a density question. I have a die that's, maybe if I have a fairly large die, and in the middle of my die, I have something very dense, like a ball bearing or something. And that ball bearing is not in the center, it's really close to one of the faces. Well, if that's the case, then that face is going to land down most of the time. Then that changes everything about that die. So we always assume, unless we have reason to believe otherwise, we assume the die is fair and that therefore all 6 faces are equally likely. So if that's the case, then the possible outcomes of rolling a pair of dice are as follows. And I find having this in my notes sometimes very useful when I start analyzing outcomes. I'm writing down all of the possible dice rolls. And there's a reason I'm doing this. We're going to get into some of the mathematics of this later, but we're going to start with the easy stuff right now. There's exactly 36 possible outcomes when I roll the die. When I roll the dice. Now, the problem is you say, well, a 5-4 and a 4-5, how are they different? Well, if it makes it easier conceptually, think of your dice as 2 different colors. Okay, one of your dice is blue and one of your dice is red. Then, oh, okay. So a blue 4 and a red 5 is different than a red 5 or a blue 5 and a red 4, but those are the possible outcomes. Now, usually when we're thinking about dice rolls, we're thinking about the total. So if I'm playing a game, I'm playing Monopoly. We're going to use Monopoly today. I'm playing Monopoly and I roll the dice. Maybe you're a craps player. You like gambling with the dice. It's the total on the dice. My wife and I play a lot of backgammon. Okay, so it's not just the individual numbers, but it's also the total on the dice that matters. So if I said, what are the possible dice totals? Well, let's see. If I add up the numbers, I could get 2, 3, 4, 5, 6, all the way up to 12. So my possible totals. These are my totals. If every single outcome is equally likely, and there are exactly 36 outcomes, then what I'd like to do is figure out what is the probability of any of these outcomes. See, the probability of rolling 4-4 is exactly the same as the probability of rolling 6-2. They're both 1 out of 36. But now I'm asking, I want the sum to be 2. I want the sum to be 3. I want the sum to be 4. These would be events. These are not individual outcomes. You see, if I want a sum of 4, I can get there this way, or this way. So there's multiple ways. So let's look at this. There's only one way to get a sum of 2. So there's 1 out of 36 probability. But there's clearly 2 ways to get a sum of 3. So that would be 2 out of 36. There are 3 ways to get a sum of 4. There are 4 ways to get a sum of 5. I think you see a pattern here. There are 5 ways to get a sum of 6. And there are 6 ways to get a sum of 7. So there must be 7 ways to get a sum of 8, right? No. It's going to start going the other way, isn't it? So it's going to be 5 out of 36, and then 4 out of 36, and then 3 out of 36, and then 2 out of 36, and then 1 out of 36. Now, something very, very important, very, very important to recognize. We said each of these outcomes is equally likely. And by the way, the outcome of 6-3 doesn't overlap with any other outcome. I mean, I got a 6 and a 3, it added to 9. There's no other outcome that has a 6 and a 3 in it. So each of these outcomes are definitely, different from each other. What happens when I add up those numbers? Anybody want to guess without doing it?
Is that 36 out of 36 or 1?
It adds up to 1. And by the way, that's a good thing. If it added up to something greater than 1, that would be an impossible situation. If it added up to something less than 1, then somehow we miscounted. So since every one of these is completely different and unrelated, it makes sense that all of their probabilities are different and unrelated, but their probabilities add up to 1. And that's huge because we're going to ask a lot of questions over time. I'm going to say, I'm going to roll the dice 3 times in a row. What's the probability of the following results consecutively? Or I'm going to roll the dice once. What's the probability that I get this outcome or this outcome or this outcome? We're going to use words like or and in the middle of things. But I want everyone to start off with this really, really basic notion of a dice roll chart, because this is very, very handy and useful, and having this this off to the side is really good. So I said, I'm going to roll the dice what's the probability that my total is odd? Huh. Anybody want to guess what's the probability that my total is odd? Well, what are the odd totals? 3, 5, 7, 9, 11.
Is it 1/2?
That's the question. Well, I could do it the long way and I could count. Does everybody agree I could just count because there's only 36 total? Okay, so 2, 1, and 1, 1. Okay, and then these guys, I could do it that way, or maybe I could just 2, 1, and 1, 1, 2, 4, 1, 3, 2, 2. Okay, all of these guys, all of these guys, all of these guys, or I could just add that, and so on. But it's going to be exactly half. Oh, okay. So if I roll a pair of fair dice and I add the numbers up, exactly half the outcomes will be odd, exactly half the outcomes will be even. What's the most likely outcome, by the way? Anybody? What's the most likely outcome when you roll?
Is it a 7?
Your most likely outcome is that the sum is 7. And that 7 is kind of special. Okay. Now, I'm not going to go into the gambling and everything right now, but for those of you who know what the game of craps is, whenever you're hearing somebody, talking about the dice, what are the two numbers they're always associating when they're playing craps? Anybody know? There's two numbers that are always associated with that dice roll. It's 7 and what? Anybody know? Good, you guys are not gamblers. That's good. 7 and 11. Okay, so the simple explanation for craps is, if I start by rolling a 7 or an 11, I win. If I roll anything other than a total of 7 or 11, well, there's not that many 11s. There's only 8 out of 36 rolls that are going to be a 7 or an 11. So that means all the rest of the rolls are not. So I roll something else. I roll a total of 9. I roll a total of 4 or 5. That becomes what's called my point. Now, that outcome is a lot less likely than a 7 or 11. So now I roll again. Whatever I hit first, either 7 or 11 or my point, will determine whether I win or lose. So you'll hear people when they roll a dice, lucky 7, 7. Why is 7 lucky? I don't know. But I do know that 7 is the most likely outcome. So that's something it's there. Well, we're going to come back to this many, many, many times over the next few weeks. This basic notion with the dice. Okay, so I'm going to erase this now. And this is a fairly simple notion. Now, what we want to do is talk about counting techniques. Now, counting techniques, that you've heard of the term combinatorics. A lot of people say, what's combinatorics? Well, counting techniques is part of what combinatorics is. It's not everything, but it's part of what it is. And your ability to count. So I can count. I learned how to count as a child. Well, I'm talking about large scale things. For example, if you wanted to buy a lottery ticket, well, exactly how many ways, can I fill out a lottery ticket? It's in the millions. So rather than write down all the possible outcomes, I just want to be able to calculate. That's what the count is. So a lot of what we're going to be doing over the next couple of weeks is calculating. So the next thing I want to go over is what's called the matching or multiplication principle. Okay, some books call it the matching principle, some call it the multiplication principle. It's the same thing. And it's the idea, I'm going to do something, and there's a certain number of ways that can happen. Now I'm going to do something else, could be the same thing again or something completely different, and the number of ways that can happen, and I'm going to keep doing this. So if I said, how many ways can I have my outcomes occur? Turns out you're going to multiply these ways, and that's not automatically obvious. So I like to start with something very important. Okay, let's consider when Mr. Brown gets up in the morning, he has to decide how to dress himself. That's a major factor of my day. So I have to choose the color of shirt, the color of shorts, and of course, the type of footwear. Okay, so I got 3 possible things here. I got shirts, shorts, and actually I don't really choose. I just take the one on top, but let's suppose it mattered. So Mr. Brown has, let's say I have 3 types of shirts. My shirts are white, black, and what would another one be? Gray. Okay, good. Most everything I have is actually gray. And let's say there are two shorts. I got to use different. And my shorts, let's say, are blue and probably gray. Let's just say green, because I need a different color there. And I have two types of footwear. I can have tennis shoes, or I can have sandals. I actually wear sandals. So when Mr. Brown gets up in the morning, he has some major decisions he has to make. You know, do I go white shirt, green shorts, tennis shoes, or something else? So how do I do this in the morning? Well, I'm going to make what's called a tree diagram. All right. So let's start with the shirts. So I have, for my shirts, the first row is going to be shirts. I have white, I have black, I have gray. I know gray and green, black and red. Don't worry about that. All right. Now that we picked the shirts, we now need to pick the shorts. So my shorts, so my possible shorts I have are blue or green, blue or green, blue or green. And now I got to pick the shoes. And I have two possibilities for the shoes. See how I did this? I had to leave myself enough room. So the possibility for the shoes, I have tennies or sandals, tennies or sandals, tennies or sandals. I don't know if people say tennies anymore, but I do. All right. Now, if I am here, what does that mean? That means I picked a black shirt, blue shorts, and tennis shoes. That is a completely different outcome than being here, which was I picked a gray shirt, blue shorts, sandals. Oops, is that right? Yeah. So every one of these positions, these terminal points, sometimes they're referred to as nodes. I don't want to get too technical. Every one of these terminal points represents a completely different attire. Okay. You can't say, well, you got the gray shirt, the green shorts and tennis shoes. That's exactly the same as gray, green, and sandals. No, that is a different outfit. If you were playing cards and you replaced one of your cards with a different card, that's not the same set of cards. It's a different set of cards. It doesn't matter that some of them remain the same. It's not exactly the whole set. So at the end, if I said exactly how many ways could I get dressed, you'd go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. But there's a much easier way of doing that. You had 3 possible outcomes here. You had 2 possible outcomes here. You had 2 possible outcomes here. And you were matching these outcomes with these outcomes. So there was exactly 6 ways that I could have done shirt and shorts. And then those outcomes were getting matched with the shoes. So there's exactly 2 ways. And it turns out I multiplied. See, when I match outcomes, I'm multiplying the number of ways of doing it. That's why it's sometimes called the matching principle or the multiplication principle. So in simple English, well, I don't know if it's simple English. Let's say you're going to perform. Okay, you're going to do, you have K events with N1, N2, NK outcomes. Okay, and they're all different. They're, you know, I put on my shirt. That's completely unrelated now to putting on my shorts, which is completely unrelated to the shoes. And now maybe I have multiple cars. And now which car am I going to get into? Now I have multiple destinations. Which destination am I going to go to? You can keep going. So if you said, how many ways can you fill out this string? It's going to be N1 times N2 all the way to NK possible outcomes. Now, you notice that's not a probability. This would be the sample space if you thought about it that way. So when I just talked about getting dressed, we came up with exactly 12 outcomes. My sample space would be ordered triples, you know, white shirt, comma, green short, comma, sandals. That would be one outcome in my sample space. And I would continue doing that process. So this gives you the number in your sample space. So now you can say at the end of the day, what's the probability that the following thing happened? And then you'd pick your specific event. So this concept is actually not only really, really simple, but it's also really easy to execute in general. So now it gives rise to the next thing. Okay. I'm going to keep it really simple. I want to arrange n distinct objects. And the distinct part is really, really important. If I said I've got 10 ping pong balls and I want to rearrange them, would any of you even know if I rearranged them? Every arrangement of those 10 ping pong balls is going to look exactly the same unless those 10 ping pong balls were 10 different colors, or each of them had 10 different patterns on it. In other words, I must be able to distinguish one ping pong ball from the other in order to do anything. If I gave you 10 identical ping pong balls, then every way I could arrange them would look exactly the same. So in essence, there'd really only be one way of doing it because it will always look the same. I have n distinct objects and I want to arrange them. To arrange means simply to put in some form of order, okay? Not random. So I might have 10 books and I want to put them on my shelf in alphabetical order, or biggest to smallest, or something like that. I have a roster of names. I want to put you in some order. What order could I put you in? Well, alphabetical is an easy one. But I could do it in chronological order of when you enrolled, based on your age. I could do it based on your height. You know, we could pick a lot of different ways to measure. But ultimately, how many ways can I arrange things? Well, I've got n objects. I'm going to put them in order. So that means there's exactly n choices for the first object. There. I have exactly n ways I can select the first object. Now the first object has been selected. There are n minus 1 objects left over. So how many ways can I select the next one? Well, it'd be n minus 1, of course. Oops. And then the next one, clearly n minus 2. Now I'm getting down to the end. I have 3 objects left. I have 3 choices. Then I have 2. Clearly I have 1. So what I just did was put n objects in order. And this is how many ways to do each of them. So if I said overall exactly how many ways could I do this, I have matched this choice with this choice with this choice. I've matched them. So the answer is I multiply the number of outcomes. That's what we just stated. So if I said, what is this product? You'd say the product is n factorial. That's where factorials really, for our practical purposes, that's where factorials come from. The number of ways of arranging n distinct objects is n factorial. That's very convenient. So regardless of how many objects you're talking about, there's no thinking. I have 10 objects, the answer is 10 factorial. I have 100 objects, the answer is 100 factorial, and so on. So the number of ways of arranging distinct objects involves a factorial. So that's a great starting point. That's a really, really easy one. Okay. So with that said, we always have some fun with, let's think phone numbers, and let's think social security numbers, and let's think of all the different types of numbers we could do and how many ways we could come up with it. So let's start with social security numbers. That's an easy one. A social security number has 9 digits. Now, you remember yours this way. Most of you remember your social security as 324. Your social security number does not have a dash in it, by the way. If I ask you for your phone number, you say, my phone number is 874, pause, 2890. The pause represented the dash. So of course, when you're dialing the phone number, you all pause after 3 digits, right? And then you finish. Or if you just entered all the digits straight through, wouldn't it still work? There's actually a reason why there's the dash in the phone number. It has nothing to do with the actual entering of the phone number. There's a reason this sequence is this way. And it has nothing to do with the importance of 3, 2. No, there's 9 numbers in your social security number, period. There's 9 numbers. There's no dashes. There's just 9 numbers. The reason actually I learned this as a kid, it has to do with your brain and your ability to recall things. And this is kind of fun because we're going to use this all throughout this chapter. If I asked you to think in your mind, think of a simple shape like a circle or a triangle or a square. Just picture a shape in your mind. Everybody could easily do that. Now I want you to picture a second shape in your mind. Okay. And picture both of them simultaneously. Okay. Maybe it's a circle and a square. Now picture a third shape in your mind. It's a little bit harder. Okay. I can picture a circle, a square, and a triangle. Now picture a fourth shape in your mind. Do you realize there are very few human beings who can do this? Very few human beings can actually picture the fourth shape in their mind. And this is evidence throughout human history. Proof. Really? Think of a deck of cards. In a deck of cards, you have you actually have numbers, right? 2 through 10. You don't have a number 1, that's the ace. You have 2 through 10. And how are the numbers? Is the 10 a sequence of 10? No, it's not. It's 3 2s and 3s, 2s, and things like that. On a die, you have the numbers 1 through 6. How is a 6 represented? Like this. Roman numerals. That's my favorite one. The Romans were pretty smart. See, you have 1, oh, right, like that. You have 2, you have 3, and of course you have 4, right? No, what's 4? What's 4?
IV.
In Roman numerals, you do realize you never have more than 3 in a row of the same symbol. The Romans figured that out because people can't see it. They can't read it. In derivative notation, calculus. Now, I want you guys to understand why we do this, because there's actually a logic, but not a mathematics. Derivative notation. I want to take the nth derivative of y, and we write that. That's a piece of cake. But what if I'm using prime notation? You don't write f. This would be really difficult to read. So after the third derivative, by the way, with prime notation, we just put the n there after the third derivative. In other words, the idea being a few hundred years ago, they realized people couldn't see. Once you put a fourth slash, 4, 5, 6, you can't really distinguish the difference. It's too difficult. So all throughout human history, we have evidence that 3 is about the most people can distinguish in a row. So we do this with other things like this. So when we're talking about arranging things, social security numbers are a perfect example. Why is the phone number 3 digits 4? Because it's too hard for people to remember 7 in a row. That's why. It's actually that simple. Why is the social security number not 3, 3, and 3 then? Because then you might get the sequences of 3 mixed up. Okay, so there's some logic to that. So now, going back to social security numbers. First of all, are there any restrictions on a social security number? This is, by the way, there are restrictions on phone numbers. Are there restrictions on a social security number? Or is every digit fair game at every position? Does anybody want to try that one? Most people actually don't know this. It's okay if you don't know it. If you don't know it, don't blurt it out then. Does anybody know, are there any restrictions on this? Are there any numbers you can't use in any particular position, for example? Anybody?
I don't think so.
That's probably the safest answer. See, with a phone number, your phone number, there's 2 numbers your phone number cannot start with. Does anybody know what those 2 numbers are? Your phone number cannot start with, there's 2 numbers.
A 1.
Or
A 0.
Because what does the 0 do? That automatically takes you to the operator. Oh, a 1 automatically means that you're now going to enter something else. Your phone number, your 7-digit number cannot start with a 1 or 0 because that indicates something else is going on. Social security numbers actually don't have any restrictions. And I always have people tell me, well, it can't start with a 0, which I find really interesting because my wife's social security number starts with a 0. Do you know what social security number the first number is based on? Anybody? It's actually absolutely simple. The first number is based on one thing and one thing only. Where were you born? The country is divided into 10 geographic regions. My wife was born in Connecticut. She has a 0. Oh, I was born in California. Mine starts with a 5. Now, I think there's 2 different numbers that Californians can start with because we do represent more than 10% of the country. So that's something there. So if I said a social security number, and there are no restrictions, then exactly how many possibilities are there for each digit? This one's kind of easy. So how many possibilities? 10 for each one. So what's the number of possible social security numbers there are? How many? Just blurt it out. How many social security numbers can we have? More than 10, certainly. 10 to the 9th. Yeah, how big is 10 to the 9th? How big is 10 in words? Nobody's walking around and say, oh, 10 to the 9th. No, that's what? It's a bazillion, right? It's a billion. Wow, that's a lot of social security numbers. But we do have a problem here because a social security number cannot be reused. Your phone number, when you give it up and you, let's say, move to a different town or you change phone providers, well, almost instantly, somebody else is now going to have your phone number. No problem. Your social security number is for life. And when you die, guess what? The social security number dies with you. Nobody gets your number again. Well, why is that a big deal? Well, I was looking this morning, we're just a couple thousand people short. We're just short of 340 million people in this country. Yeah. That's 340 million different social security numbers, but there have been people who have died over the last century. In other words, we've used way more than half of all possible social security numbers. I don't know the date, but I know time is running out before we've used up every single social security number. And then I don't know what we're going to do. Maybe we're going to add a digit. I don't know. We will run out in a finite amount of time because we're not reusing any of them. Now, phone numbers. Let's have some fun. Now, we agreed you cannot start a phone number with a 0 or a 1. So how many possibilities for the first position in the phone number? Take memory.
9.
We can't start with a 0
One.
or a 1.
You can't start with a 1, so it's 8.
Yeah, your individual phone number. So phone numbers, 1, 2, 3, 4, 5, 6. Wait, 10 to the 6 is only a million. Okay, we have a problem here. There's only 8 million different legal phone numbers. 8 million? How many people are there in San Diego County alone? I mean,
4 million, maybe? 4 million?
I don't know if it's that many. It's more than a couple million. Okay, so why is that a big deal? Everybody you know has a cell phone, probably. I have a cell phone. My wife has a cell phone. My kids all have cell phones, and we have a home phone. And I have an office phone, and my wife has an office phone. Businesses often have many, many phone numbers, and they're not even counted as individuals. In other words, in San Diego County alone, do you know how many different phone numbers we have? Now you're probably at least this many, if not more. That's a problem. If we can't share the same phone number, see, if AJ and I have the same phone numbers, it can be very confusing when you want to call him and you reach me and vice versa. So how do we handle the problem of the fact that there's so many people and not enough phone numbers?
Area codes?
Area codes. That's why they exist. What do area codes do to this? The area code is a 3-digit number in front. And area codes, I don't believe, have any restrictions at all. But area codes now just made that 8 million into 8 billion. Oh, okay. So we're probably okay in the US because we can reuse phone numbers. But if you said worldwide, oh, there's a lot more than 8 billion phone numbers worldwide. So then what you have are international numbers. That's where you have the 00 in front of your phone and all that. If you've ever called somebody in a foreign country, right, that's, you hit 0 twice, that kind of thing. But we figured it out on phone numbers. Now, license plates, those are always fun. I actually got my driver's license in a time when license plates had 3 numbers and 3 letters. How many digits, how many things are on your license plate? Anybody know?
At least in California, 7.
7. Well, why would there be 7? All right. Well, if you can have 3 numbers, and I'm not talking about specialized plates where you wanted to put a really cool word, God, that is so old. You know, everybody like, what about my cool specialized license plate? No, let's take that out of the equation. A license plate generated by the DMV. How about? Well, how does this work? It's 3 letters with no restrictions. And by the way, we're talking about, you know, people say, well, you can't have profanity. If you got 3 letters, you're a lot less likely to have profanity. Okay. So you have 26, 26, 26, 10, 10, 10. Can you reuse a license plate, by the way? Can a license plate get reused? No. Again, dies with the car. So right now, this is where the time I grew up, there was 26 times 26 times 26 times 10 times 10 times 10 possible license plates. So, well, that's a lot of license plates. You're right. That's a lot of license plates. That's 17,576,000. I'm pretty sure there's a lot more than that many cars in California. I think there's that many cars in San Diego practically. Oh, so there was a time we didn't need more than this, but the moment we realized we have more, what did we do? We added a digit. And the funny thing is that digit keeps changing. So every time a new car, so what's going to happen eventually, by the way?
We're probably gonna add another number or
Probably gonna add another digit, yeah. And by the way, you'll say, heck, I have a car that only has 7 digits. You know, I've got an old classic. Well, you don't see a lot of cars, at least I haven't at any time recently, where it only had 6, because it's been a long time since we added that other digit. So this is, by the way, I'm not listing all the possible license plates. I'm not listing all the possible social security numbers. I am counting them. That's what combinatorics is. The ability to count those results. Now, we listed the coin flips, we listed the dice rolls because it was a very small, finite quantity. Always list them when it's small because then it's easier to conceptualize. But if I'm asking a really, really large calculation, no, it'd be foolish to try to list them all. I mean, you know, when the answer's in bazillions and so on. So now, the next thing I want to go over is, let's start something simple. Let's say just for fun, you said, I want to make up a 7-digit phone number without restrictions, just for fun. You're going to make one up. Okay, without restrictions on the first number. But no digits can repeat. So you want a phone number where no digits can repeat. So maybe your phone number is 1 2 3 4 5 6 7. That's your phone number. Or it's 2 4 6 8 1 3 5. You know, whatever. You have a phone number where I'm not putting no restrictions on the first number whatsoever. And you can't repeat. Well, let's see. What would that look like? If there's no restrictions on the first number, then I have exactly 10 choices for my first number. Then after I've selected my first number, then 9, then 8, then 7, then 6, then 5, then 4. Great. So I want to multiply that out. And if I multiply that, but it's going to take me a moment. But if I multiply that whole thing out, I eventually will get 604,800 different phone numbers that have no restrictions on the first digit, and I never reused a number. Okay, that's just for fun. My point being, I had to enter 10 times 9 times 8 times 7 times 6 times 5 times 4. That's really inconvenient. I would have loved to use a factorial, but that's not a factorial, is it? Do you agree?
Professor, is 10 a digit? I thought it's not a digit.
No. Your digits are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. There's exactly 10 digits.
Yeah, but why did you start with 10?
How many digits are there from 0 through 9?
10.
And so how many choices do you have for the first position on your phone? 10.
10. But why do you have 10 as the first number, not 9?
When we did the license plates, there's 26 letters, so you had 26 choices, right? You have 10 digits available, 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9.
But 10 is not a digit.
No, 10 is how many digits there are. Your phone number isn't 10, 9. No, there's 10 choices for your first digit. Pick a digit. Now, you've used that digit, pick another digit. Now you've used that digit, now pick another digit. There are 10 possible digits. If I said we're going to do this with letters, you'd say there are 26 letters. 26 is not a letter. No, 26 is how many letters there are. 10 is how many digits there are.
Yeah, but why the first digit of the phone number you wrote down is 10?
That's not the phone number.
If I said how many coins are in your pocket and you said I have 13 coins in my pocket, but there is no coin worth 13 cents, that you see you're kind of mixing things. How many numbers are there possible? How many numbers? Not what is the number, how many numbers?
10.
There are 10 possible choices. That's what 10 represents.
Okay.
You're never going to multiply. If I said my number is 2468135, you're not multiplying those numbers. No. You're not multiplying your phone number. You're saying how
Okay, I
many
get
numbers
it.
are possible. Okay, now it'd be great if we could do this as a factorial, but we can't. What if I did this? 3 times 2 times 1. Well, I can't do that unless I divided it by that. Would that be legal, what I just did? Would that be legal to multiply by 321 over 321? Anybody? Is that legal mathematically?
Yeah.
Yeah, why would I want to do that? Because now my answer is 10 factorial over 3 factorial. And that would be so much easier and so much faster to do on my calculator. You see, what if we had a really long string of numbers and I had to multiply a lot of numbers, but not all the way down to 1? Well, where did the 3 come from? I don't see any 3s up here. Where did this come from? Wouldn't this be the same as 1, 2, 3, 4, 5, 6, 7? I had 7 slots to fill. That 3 factorial that I need, this was actually because it was 10 minus 7. So this is actually what this problem suggested. I have just from 10 different digits, right? Would you say 0 through 9 are clearly distinct? Remember I said when you're arranging n distinct objects, I'm arranging 10 distinct integers, the numbers 0 through 9, but I'm not arranging all 10 of them. I'm leaving 3 of them out. So I'm selecting which 7 of them I want to arrange. This is called a permutation. Now, this is actually a common English word that I would venture to say the vast majority of times outside of a math class, you've ever heard somebody use the word permutation, they completely misuse the word. I hear people, I watch sports all the time and announcers love throwing in all the different permutations of blah, blah. They have no idea what they're saying usually. The word permutation, it's a noun, it means arrangement. Literally, it means arrangement. To permute, that's a verb, that means to arrange. Permutation is the result. A permutation is an arrangement. But the term arrangement implies that you can distinguish. Remember, we talked about arranging ping pong balls? There's only one way because they all look the same. So to have a permutation, I must have objects that I can distinguish. Otherwise, there really isn't an arrangement going on at all. So when people use the word permutation, if they're not using it to mean arrangement, then they're just making it up, because that's what it means from an English standpoint. A permutation is an arrangement. So if you said you have n distinct objects, choose R to arrange. And arrange, another way of thinking of arrange is, that looks terrible, put in order. That's what arrange means. You're actually putting them in an order. It's not just randomly scattered, so I can line them up if you want. So I have n distinct objects. I'm going to choose R. Clearly, R must be less than or equal. R, I can't have more. I have 10 numbers. I want you to choose 15 of them. No, I don't have 15 to choose. I can choose a number less than 10 or 10 itself. And the way we often write, there's three ways that you will see this written. All of them are correct. And a lot of times it just has to do with the font of the textbook. You'll see P, N choose R. You'll see N capital P R. You will see P N R. This one's the most likely on your calculator, or even this one. Now I've got a little cheapo calculator here, and my calculator has this, but I also have a calculator that writes it this way. And in textbooks, it's usually written this way. It's the same thing. Permutation of n objects, choose R of them. And that number is simply n factorial, n minus R factorial. And it's a very, very simple calculation. Very simple calculation. But this is how many ways you can arrange something. Now, what if I chose all 10? I want to have all 10 digits and not repeat any. Well, then obviously that answer would have been 10 factorial because I'm arranging all 10. So if we said permutation of n choose n, wouldn't that be n factorial over n minus n factorial? What do we know about 0 factorial? Anybody know?
It's 1.
0 factorial is 1. Most math classes will tell you 0 factorial is defined to be 1. And I'm okay with that. That's not correct, by the way. Has anybody in this class you've completed differential equations? Math 255. Has anybody? You can say yes or no. I'm not going to make you do something. If you've completed differential equations, then you probably, God, I hope you worked with the gamma function. That's a really, really important part of DiffyQ. The gamma function is where factorials come from. 0 factorial is a calculation. It's not a definition. There's an actual physical calculation in an integral. 0 factorial is calculated to be 1. But unless you've had differential equations, you would have never seen the formula that produces that. So in lower level math classes, we just tell people, yeah, 0 factorial is 1. That's a definition. Don't worry about it. Well, I don't like the don't worry about it part, but obviously this has to be 1 because I already know if I'm taking n objects and arranging all n of them, my answer has to be n factorial. And the only way my answer can be n factorial is if that quantity is 1. And later when we get into combinations again, you'll remember that, oh yeah, 0 factorial comes up a lot in combinations, and 0 factorial is 1. It's not 0. That would be a problem. Okay, so permutations are actually, they're kind of cool. They're not difficult, but it's also something that we like the notation because it makes it easier for us to do. I'll give you an example. If you have a cheap calculator, and by a cheap calculator, I mean a non-graphing calculator, something that's fast and practical. Does anybody know the upper limit on your factorials without, don't cheat, don't do it. Does anybody know what's the upper limit on what you can enter in your calculator? They're all the same, so. It's 69. 69 factorial is the biggest number you can enter in your cheap calculator. That's it. I mean, infinity is really big. 69 factorial, that's kind of tiny. I have a TI titanium, I can go up to 449 factorial on mine. And the reason is your calculator's ability to store does not go past 10 to the 99th power. It won't store up to 10 to the 100th power. Mine will go up to 10 to the 999th power. But that's still not very big, in the big picture. So let's say I have 100 objects and I want to put 90 of them in order. I have 100 objects and I want to put, not 90, I'm sorry. I have 100 objects and I want to put, 10 of them in order. So I've got 100 books and I want to grab 10 of them and then put them in order, put them on display, whatever. Could be in a grocery store. I have 100 objects on the shelf and I want to take 10 for an end cap and put them in order. Well, I know that the answer to this is 100 factorial over 90 factorial, but my calculator is not going to do either one of those. Those are way beyond what my calculator can do. But here's the great part. I'm going to go ahead and enter it anyway. 100 permutation 10 equals. Wait a minute. How did how did my calculator do this when it can't do either one of those? How is that possible? Because this is 100 times 99 times 91 times 90 factorial over 90 factorial, and I can do that. So the answer my calculator gave me was 100 times 99 times 98 down to 91. And that's not that big of a number. So one of the advantages of using the permutation key as opposed to the factorial key is I could not have individually done numerator or denominator on my cheap calculator, but I could do this on my cheap calculator. And that's one of the things you like. Now, if you have a fancier calculator and you've got to go into menu options and all that, the way your calculator is doing a permutation is it's already doing the cancel. It's not independently calculating numerator and denominator. Not only would that take a long time, it's beyond the level of your calculator, but it's giving you what the quotient is, and that's what you actually want. And the permutation has to be a positive integer. It can't be a decimal, it can't be a fraction, and it certainly cannot be negative. So permutations are a very fast way of doing a count. They're not the only way, and they're not actually the most important of the combinatorics. They're just the first one because they go directly with the matching or multiplication principle. All right, so I'm going to stop there.